Hi everyone, my name is Stella, and this is our first video with Math Club, and we're in Bruin together. Can you guys introduce yourselves?
So I'm Olex.
And I'm Isaac, the treasurer of Math Club.
hmm And today our plan is to go over just ideas on the function and also how to translate functions into graphs. So I'm going to start us off with what exactly a function is. So in CPM chapter 1, which is what we're basing our videos off of, it introduces the concept of a function to you through the function machine. So basically it's the idea is you put something in a box and then you're going to get something out of it. So let's say you put a number n inside a box and the box tells you n plus 3. So then from here, you would just get the value of what n plus 3 is, the output. So if we were to put in n equals 2, we'd get out 2 plus 3, which equals 5. So in this case, the input would be 2, while the output would be 5. And to write this in a more like mathematical format, Alex.
So specifically you can write it as f of n, which basically tells you that you're doing something to n, and f is what you're doing to it, is equal to n plus 3. So this f of n basically describes what the function machine does.
Mm-hmm. And also a side note that this variable is what we call is like the what you put inside the f. So the f is a function, n is the variable. Normally, because most people use x as like a common variable, you'll find f of x a lot, but it depends on what this variable is that will determine what goes inside the function, or vice versa.
And I just want to add additionally is looking at this machine, what makes this specific machine a quote unquote function is that you will never get two possible outputs for the same input. So each input will only give you one output.
Mm-hmm. So to define a function, it means every, like Oleg said, every input has a specific output. If an input has multiple outputs, in that case, it wouldn't be a function anymore.
So looking at this expression right here, some of you might not recognize this expression. And first of all, it's because oftentimes instead of using n, people use x. So they write this as f of x is equal to x plus 3. And this would be equivalent. It's just you're changing the name of the variable. Also, a lot of times people just choose to replace f of x with y. And all of these pretty much equal the same thing.
And with that, we are going to go into how these kind of functions, or like the y equals x plus 3, will show us what a graph will look like.
These are some of the examples of functions. And in a graph, you have the y-axis and the x-axis. And so in a linear function, let's go back to, let's say fx equals x plus 3, or in this case, y equals x plus 3. When x equals, like, say 1, then y would equal 4. X equals 2, y would equal 5. And if you keep on doing putting points like this, you can see that when you connect all these dots, it forms a straight line. This is what we call a linear function. It's when the x part here, it has its power is 1. It's not x squared or anything like that. It's just x. But this is what a linear function would look like. A and b are variables. They can be anything. And the power value, the exponent, will always be 1 for a linear function.
Function will always be a straight line.
Mm-hmm.
Okay.
And also,
oh yeah, go ahead.
sometimes when a equals 0, then you would get like y equals b. This would be a vertical line. No, it's a horizontal line. So it's a straight horizontal line at b, and uh, if if the if this was the function and there's nothing else, then this would be a vertical line at x equals 4. But yeah.
Wait, we can't say the vertical line is a function because it's not.
No, Isaac, that's
Oh,
not a function.
I was testing you. That's what you shouldn't be doing.
So as Isaac talked about linear functions in the form of y equals ax plus b, there's also other functions, and there are different names for them. So for one of these types is functions in which the power of x is more than 1. So for example, y equals x squared. These functions are called exponential. So y equals x squared, y equals x to the third, y equals x to the fifth, whatever. As long as the power is greater than 1, these functions are exponential. And in general, you don't really need to know how to graph them exactly right now, but we can just plot some points. So example for y equals x squared. Well, when x is 1, y is also 1. So there'll be a point here. When x is 2, y is 4. There'll be a point in here. And then we can do x equals negative 1. Negative 1 squared is also 1. So it'll be a point here. X is 0, y is 0. So a point like here. And overall, the function will look something like this. And this looks like a parabola, which is why function in the form of y equals x squared. So it's if the functions have an x squared in it, and x squared is the largest term, then they'll look like a parabola. And these are called parabolic functions. For y equals x third, I'm going to not bother plotting all the points, but the function kind of looks like this. For x to the fifth, they get more complicated, but these are the main two.
So the last type of function that we are going to look at is absolute value function. So we would write this as either f of x equals the absolute value of x. This is just the most basic form. Or same thing as just y is equals to the absolute value of x. So we'll talk about, so the equation for an absolute value graph is an expanded form is a x minus h and then plus k. We are going, for sake of simplicity, we are going to imagine just, for this example, just if a and h and k were all 0. So, I mean, if a was 1 and h and k were 0. So just this function. And how we would graph that would be, so this is x, y. So if we were to plot something, if x equals 0, y equals 0, x equals 1, y equals 1, x equals 2, y equals 2, and then x equals negative 1, absolute value means just the distance it is from the origin, or 0. So when x equals negative 1, y equals 1. And in the end, the graph will look something like this. And as just a pre-note, unless a, we'll go further into this in future videos, but when a is positive, the entire f of x will be above the x-axis. And then if a is negative, then the opposite. So f of x will be below the x-axis. And h and k don't do anything except move the entire f of x either to the right or up and down. So just directions, but we'll go over that later.
Okay, so here are some examples of these functions. So for a, let's get this out. It's not perfectly, it's not perfectly looking, but it'll do. So right here, it's an example of an exponential function, right? We would call this a cubic function. And it looks kind of like this. Wait, ignore, let me just erase that part. Kind of looks like that. Oh, yeah. when x equals 0, y equals 0. When x is positive, y is positive. When x is negative, y is negative. It's going to keep on going to go up and down. That's because in a cubic function, um, if if your number is negative and if you cube that number, it's going to be negative. And if your number is positive, then and you cube it, it's going to be positive. So that is what that would look like. B, x squared plus 3. I believe this would be looking like, and feel free to correct me. I think this would just be a normal quadratic function. That's also a name for, a function with a power of 2, and it's going to be up by 3. It's up by 3 because right here, this number increases. So in actuality, without this, and x equals 0, then y would equal 0. But because it plus 3, it raises the entire function up by 3 units. Yeah.
Let's look at C. So for this one specifically, let's try graphing some of the points to see what it is. Okay, so when x equals 0, it's -5. So that's somewhere here. -5. When x equals 1, it's -3 because 2 minus 5 is -3. So somewhere here. And when x equals 2, it's -1. So somewhere here. And I think you guys are noticing a pattern. It'll just keep going in a line like this. And if you notice, as Isaac said, this -5 brings this line down by 5 units from what it would have been before. And this is because at each point of x, without the 5, x would be 5 above. So if you're just bringing down all the points by 5, it's equivalent to bringing down the whole line by 5, which is why adding this -5 moves it down by 5. Now let's look at D. Let's do the same thing for D. Let's try graphing some of the points. So at 0, f of x will be 1. So it'll be somewhere here. At -1, it'll be 0 because -1 plus 1 is 0, absolute value is 0 is 0. At -2, it will be also 1 because -2 plus 1 is -1, and then absolute value of -1 is 1. And then at 1, it will be 2 because 1 plus 2 is 2, and then absolute value of that is 2. And it'll basically be like what you guys saw at the start, where it's like kind of like a V shape. However, if you guys notice that this V shape is translated 1 to the back, and this is because of this +1 here. As you guys will find out later, adding this +1 will actually move the functions to the left and to the right. And to get a kind of conceptual understanding of what the +1 does, well, basically all the values that were 1 less than the values before end up giving you the same value, which is why the function is actually translated to the left by 1.
And looking at E, we have f of x equals negative, the negative absolute value of x. So in a graph, if we were to plot down some of the points, we know that the absolute value of x itself is just going to look something like this. But because it's negative, we want, if x were to be 1, then we would get -1. If x is 0, we get 0. If x is -1, we still get -1. And so the ending graph would look something like this. And for f, we have, so looking at the equation f of x equals 4 times x, we know already that this is a linear function because there's no, the power of x is 1, not anything greater. So, or less. So if x were 0, then we would get 0. X was 1, we would get 4. Just gonna drop it here. If x is 2, then we get 8. 4, 8, and then x is -1, we would get -4. And we connect all the dots, we would get a straight diagonal line. And from here, I'm going to explain what domain and range are. For domain and range, let's look at this. Let's look at what we have for E as an example. Domain is the values of x that are present in a graph, and range, so let me write this. Domain is x values, and range are the y values, So for f of x equals a negative absolute value of x, looking from the graph, we can see that the x values, this side is going to go forever to the left, so negative infinity, and this side is going to go forever onto the right, so positive infinity. In that case, we would say domain is, you could either write all real values, and for range, we can see that there are going to be y values from 0 to negative infinity, because these will forever go down. However, we don't see any values in the positive y coordinates. So we would say less than or equal to 0. And let's do, so for f, we use the same process. So first we know the graph is 4 times x, domain, all, so we want to see how many x values are present. Looking at this graph, this going to the left side, it will forever go down and to the left. And looking at the right side, it'll go forever upwards towards the right. So we know that the domain is all real values. And how about the range? So range is also all real values, because we know that this side will reach towards positive infinity, while this side will reach towards negative infinity.
So let's go back to the functions you guys, or the type of function you guys will see the most, and this is the linear function, y equals mx plus b. And in here, b and m can be any number. And in general, these functions will kind of look like a line. And what you will notice is if you change m, if you make m bigger, then line will get steeper and steeper. So kind of like this. And then changing b will basically move the line up or down. So let's try to see if that's true. So let's have y equals 1x and y equals 2x. And we'll graph y equals 1x, 2x. We'll graph y equals 1x in blue and the other one in red. So with y equals 1x at 1, the function is also 1. At 2, the function is also 2. And it kind of looks like this. Now with y equals 2x, they're both 0 at 0. But at 1, y equals 2x is 2. And in this case, the function will keep going up that way. So as you notice, y equals 2x is actually steeper. And if you were given a graph without knowing what the slope is, or without what m is, the way to calculate m is a really popular saying, rise over run. And this is super important. But basically what you do is you pick any 2 points, you find the difference in y between the 2 points. So let's say for this function, I'll pick 1, 1, and 2, 2. The difference in y is 1, the difference in x is 1. So the amount this function rose is 1. And then the amount this function ran is also 1 because the difference in x is 1. And so we know that for this specific function, m is equal to 1. Now let's look at y equals 2x. Let's say I want to pick a point somewhere here. So let's say I want to pick 1, -2, and then also this point. So from 1, -2, or from -1, -2, the function runs 2 units and it goes up 4 units. So if we can write that as 4/2, and we'll notice that m equals 2. So in this way, you can easily go from a graph of a line to its function, and also the other way around.
So in a function y equals mx plus b basically raises the function, say b equals 3, and let's say y equals x plus b, right? Then it would be increased by 3 units. It just kind of like raises up, right? And say b equals -3, same function. Then it would be lowered by -3. Basically, the rate still stays the same, the slope still stays the same, but all that's changed is that the function is just raised or lowered by that amount of units. So to further emphasize kind of what b is essentially, let's say that this is b equals 3 here. Normally, for just y equals x, at x equals 0, obviously y would equal 0, right? But because b equals 3, this is now 0, 3. Likewise for b equals -3, right? Now it's 0, -3.